Hello, and welcome to another session on sequential circuits, this time focusing on SR or set reset latches. As a review, sequential circuits are logic circuits which depend on a previous input or output, as well as the present inputs to determine the new or next output. The sequential circuits that we're covering will be exclusively synchronous, meaning that they are controlled by a clock such that the outputs can only change under certain conditions of the clock signal. Since we have a latch, that means that the output of the SR latch will only change either when the clock is high or is at a positive level, or when the clock is low or is at a negative level. This example here in the timing diagram is a positive level triggered SR latch. And we can tell that because the output, Q, only changes when the enable signal is high. That makes it positive level triggered. The SR latch has three functions: set, reset, and hold. When S is 1 and R is 0 and enable is high, then the output goes to 1. When S is 0, R is 1, and the clock is still high, as the output Q goes to 0. And when S and R are both equal to 0, the output Q just holds its state. And after the clock drops low again, the SR latch output Q remains in its hold state. So let's take a look now at what that looks like in terms of our symbol and our truth tables. The symbol for the SR latch shows an enable signal. That in this case, since there's no symbol right here where enable is located, that means that the latch is positive level triggered and will only change when the enable signal goes high. The functional truth table to the right tells us what's going to happen for certain combinations of the input. When enable is high and S and R are both 0, that means that the outputs will hold. Whatever Q and Q0 are at that time, they will just hold their values. When the input S is 0, reset is 1, the outputs go into a reset state where Q is equal to 0 and Q0 is equal to 1. And when the opposite is true, S is equal to 1 and R is equal to 0, that induces a set state where the output goes to 1 and the inverse of the output goes to 0. And finally, when the clock is high and when S and R are both 1, we get an output that's not true to Q and Q0, which we'll take a more detailed look at later. And when enable is low, the latch is not active, so regardless of what S and R are, the latch goes into a hold state and the values of Q and Q0 remain constant. Now the complete truth table for all possible input combinations of S, R, and the output Q and its inverse is shown here in this slide. And we've just shown the same thing here. This complete truth table assumes that enable is high and the output can change. And for S and R equal to 0, we know that's our hold state. So the values of Q and Q0 in their present state are identical to that in the next cycle or the next state. When S is equal to 0 and R is equal to 1, we're in a reset state, described functionally here by this line in the functional truth table. And then when S is 1 and R is 0, we go into the set state rather than the reset state. And finally, the last combination, S and R equal to 1, is not allowed, so we ignore what's going on there. To better understand how this truth table came to be, let's take a look at the implementation of an SR circuit or an SR latch that begins with the basic set-reset circuit shown here. Now to analyze this circuit, we'll analyze every possible combination of the inputs. And since there are only two inputs, R and S, or reset and set, we'll only have four possible combinations, and we'll just analyze those one at a time. So let's take a look first at what happens when R is equal to 1 and set is equal to 0. In that situation, what happens is we take a look at the NOR function to understand how the outputs are controlled. So the NOR function tells us that anytime there's a 1 at one of the inputs, whether either or both of the inputs, the output is 0. And only when both inputs are 0 is the output equal to 1. So in the case of NOR 1, R equals 1 forces the output to NOR of 0 because every possible input combination when one of the inputs is 1 results in an output of 0. Then we know that the 0 NOR 0 will give us an output of 1. So we've proven here the reset condition, that when reset is equal to 1 and set is equal to 0, the output Q resets to 0 and Q naught is the inverse at a value of 1. Now we can keep going. The next combination we'll look at is when S is equal to 1 and R is equal to 0, which is the set condition. And let's verify that it's actually setting the output to equal to 1. So when S is equal to 1, because of our NOR function, we know that the output is automatically 0, regardless of what the other input is. And once we know Q naught is equal to 0, we know that reset has been set to 0, and 0 NOR 0 is equal to 1. And that gives us our set condition with Q equal to 1 and Q naught equal to 0. In the next condition, we can look at set and reset both equal to 0 and see what happens. So when set is equal to 0 and reset is equal to 0, we know that the output of the NOR gate is going to be completely controlled by the other input. In this case, it'll be Q naught. So we know that if Q naught is equal to 1, the output of the NOR gate will be 0. And if Q naught is equal to 0, the output of the NOR gate will be 1. Therefore, the output of the NOR gate is simply Q. And likewise, we can use the same reasoning down here at NOR 2 to discover that the output is simply Q naught at NOR 2. And that means that no matter what Q and Q naught are, they will simply hold their condition when R and S are both 0. And that's the hold condition. Finally, let's look at what's going on with S equal to 1 and R equals to 1. When these are both equal to 1, we know that the output of the NOR gates are both forced to 0, because anytime there's at least one input to a NOR gate that's 1, the output will go to 0. This makes both Q and Q naught equal to 0, which is certainly possible, but it violates our intended design of this circuit for Q naught to be the inverse of Q. And that's why we say SR equal to 1, 1 is not allowed. It's something we want to avoid to violate the design intent of this SR latch. So that's where our not allowed condition comes from. And we would design the circuit such that set and reset are never 1 at the same time. So we've looked at all the possible combinations of the SR circuit and discovered that we have 3 possible conditions and 1 not allowed condition. We have a set condition, a reset condition, and a hold condition. And that's what makes up the SR circuit. But how do we now turn that into a latch? Well, we have to add an enable signal. And this is what that looks like. Now when we add an enable signal, the inputs to the SR latch are going to be 0 anytime that enable is equal to 0. So in order for this latch to function properly and receive the values of R and S, enable will have to go high. So this latch enables the SR circuit that's in the latter phase of this diagram to work only when enable is in a high state. And that's how we simply make an SR latch with an SR circuit. Now we can also convert this to a purely NAND gate implementation by inverting the output of each AND gate and the inputs to the next NOR gate. But when we do that, we'll have an extra inverter here. So if we invert this now, this will have to turn into Q. And if we invert this input, this will have to turn into Q naught. And at the output now, to make a NAND gate, because an OR gate with inverted inputs is equal to a NAND gate, we'll have to switch the outputs Q and Q naught. Now you can work this out on your own, but the bottom line is that the NAND gate implementation looks very similar to this implementation, with 4 NAND gates and the S and R now flipped to generate the correct outputs at Q and Q naught. And you can prove that for yourself using De Morgan's theorem. So this is how we make a set-reset latch that performs either on a positive level of the clock signal or the enable signal, or the negative level when the enable signal is low. This provides the ability to set a wide variety of logic circuits or reset them to a given state. And it's very important to use these SR latches to create predictable power up and power down conditions in digital circuits, and also to resolve potential glitches and other erroneous signals that come about in digital systems. And like other latches, the SR latch functions only in certain states of the clock or enable signal, whether positive or negative level. Well, that's all today for SR latches and SR circuits. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.